Swayam Prabha. Digital India. Educated India.
So now what remains to be shown is that R has a closed graph. Okay. Now go back and see what is the definition of a graph of a set valued map. Well, a graph is y comma z such that z belongs to R of y, okay, and y belongs to y. Okay, it's all of this whole thing, this cloud of points here was the graph. This graph has to be shown to be a closed set. Which means what? If I take a sequence of points in this set that converges to some point, then the limit should also be in this set. Okay, which means and remember R itself is a tuple of best response, is a Cartesian product of best responses. So if I take what am I taking then? When I take a sequence of points, I take a sequence of y's. And a corresponding best responses to the y minus i's from that sequence. Okay. So, I take a sequence of y's here and corresponding to that I am also taking for each y I take a z belonging to R of y, which means I am taking one best response for each player. This is my sequence. This sequence suppose converges to some point. Okay. Question is that point such that the y coordinate of that is in capital Y and its limit is also a best response. Okay. So, that is all that we need to show. Okay. So, alright. So, now let us come to part 3, which is showing that R has a closed graph. Now, what we need to show is that if, so what we will do is we can actually go again step by step. We will first show Ri as a closed graph. Before we show R as a closed graph, we say Ri has a closed graph for every I, and then because it is a Cartesian product, once again we will get the closed graph property will transfer also to the Cartesian product. Okay. Now that part is fairly standard, but I will let us just do the Ri part first, and then after that we can you will see how it will follow for R as well. Okay. Okay. So, show that if we will show Ri has a closed graph. Okay. We need to show this, that if you have a y minus I k converging to some y minus I and a yi k sequence converging to some yi, okay, such that each yi k is a best response to y minus I k, then yi has to be a best response to y minus I. So, what do we need to show? We need to show that if you take a sequence like this, y minus I k tending to y minus I and yi k tending to yi, and where yi k is a best response to y minus I k, then the limit yi is also a best response to y minus I, right. Okay. Now, to do this, let us do the following. So, let us fix a yi dash in capital Y. Okay. Now, if you I am fixing this yi dash in capital Y. Now, since yik is a best response to y minus ik, I have this property. I have that ji of yik is better than playing. So, this is better than playing yi dash, assuming others still play y minus ik. So, if I am fixing a yi dash, some particular strategy here. Now, yik is a best response to y minus ik, which means it is better than playing yi dash, okay, in response to y minus. While others play y minus k, I would want to play, player I wants to play yik. So, this is better than, since this is a best response, this is better than playing yi dash. Okay. Now, this is true for every point k along that sequence. Okay. This is true for every point k along the sequence. Okay. Now, so then what we can do is now take limit as, take k going to infinity. I am fix a yi dash. So, yi dash does not move with k. Okay. So, I take the limit as k tends to infinity. Tell me what do I get when I take the limit? So, we just said that ji is actually a polynomial, right? Ji was this polynomial. So, it is therefore a continuous function of its argument. It is a polynomial in y1 to yn, so it is therefore continuous in y1 to yn. So, therefore, when I take this limit here, when I take the limit here as k tends to infinity, limit k tends to infinity here, this is going to be limit as k tends to infinity yi dash comma y minus ik. Now, what is, since ji is continuous as a function of its arguments, this limit basically goes inside. Okay. So, what I will get here is that ji, here I am going to get ji of the limit, which is yi comma y minus I, that is less than equal to ji of yi dash comma y minus I. Is this clear? Now, this, remember, I did this for a fixed yi dash, but then this can be done for every yi dash. I can repeat this procedure for every yi dash, which means that I have this particular statement here. This actually holds not just for the yi dash that I did, this holds for every yi dash. In other words, this is true for every yi dash. Now, if this is true for every yi dash, what does this inequality basically say? It is saying that yi is a best response to yi dash, y minus I, right. So, this is effectively saying that yi is a best response to y minus I. Okay. So, once again, let us see what we did. We took a sequence y minus ik comma yik. Yik was a best response to y minus ik for every k. Their limit was y minus I and yi, and what we showed was the limit, in the limit also this best response property holds. So, yi is a best response to y minus I. Okay. All right. Okay. So, what does this mean? This means that if you take a sequence of points that are in the graph of Ri, their limit is also in the graph of Ri. Okay. These points yi comma y minus I, yik comma y minus ik were in the graph of Ri because of this reason, because of yik being a best response to y minus ik. Okay. So, which means therefore that the graph of, which means Ri is closed. Okay. Now, we can do this collectively also for R, because R is itself a product of R, of the Ri's. The argument is a little bit subtle. I don't want to sort of confuse you, but essentially what you do is you do it for the first player, then by taking some sequence, like you take some sequence, do it for the first, show that it's closed for the first player, then you can take a subsequence of that sequence, along that subsequence do it for the second player, and then take a subsequence of further subsequence of that, do it for the third player, and so on. And in short, you will be able to show that the limiting point is actually in the graph of R, R itself. So in short, the graph from here you will basically get that when the graph of Ri is closed, the graph of R is also closed. Okay, so graph of R is closed. Okay, so now, so again, let's go back and check what Kakutani was asking us to do. This is what we have therefore now accomplished. So now we have ticked off 1, 2, 3, 4, and so hence we have from Kakutani, there exists a fixed point for R, which means there exists a Nash equilibrium. Okay. So this basically shows that there is always a Nash equilibrium if we move to mixed strategies, which means again what we have now pushed the theory of games even further. Earlier we didn't have, the way we started was we tried to solve games using dominance, but then dominance you couldn't always eliminate strategies and get to a solution. We then moved to mixed strategies. We looked at in zero sum games. There we found that there is a saddle point. But then that's not all the class of games. There is a much more general class of games which is non-zero sum games, and over there also there is a Nash equilibrium. So there is something that we can call as a solution for a game for all of these games now. Okay. So what this is effectively done is we started off with this idea that you could take a game and we could come up with some kind of a notion of what we can say is the outcome of this game, right. But for that notion to actually work out, it needed to satisfy the mathematics that we specify it with. But a pure strategy did not, and that became a hurdle, but a mixed strategy does. There are two things I should mention. First is we assume just finitely many strategies, so this can be generalized vastly. Okay, you can allow for more general strategy spaces and so on. Okay, this is just a beginner level proof for you guys to see. There mathematically much more general results are known. Secondly, the Nash's contribution is not the proof, it is the concept. Okay, the proof was not, the proof actually is fairly elementary. In fact, if you have some experience in analysis and fixed point theory, you can more or less see that such a point should exist. But why should you be looking for such a point is the question. Okay, therefore the concept is the important contribution, and not that. Of course, you need to back it up with the proof of existence, otherwise the concept becomes vacuous. But proof by itself is not the achievement. Okay, so let me also mention one other point which kind of came up as we were doing this proof. We saw that R is convex valued, which means that and each Ri was the solution of a linear program. Since it's a solution of a linear program, and since and look at the constraints of the linear program, the constraints are that it's just a probability distribution. Then exactly the same thing that we saw in the Sherlock Holmes problem or in general in zero sum games holds here also. So assuming the others play y minus I, the optimal thing for player I to play there would always be a pure strategy that is optimal for player I to play, because he will obviously pick the one that has the largest weight, or in this case the minimum weight, right, because he is minimizing, right. And that's because these constraints are all, they just define a probability distribution. So effectively he is just taking a weighted combination. So the y minus i's, in response to those y minus i's, a player should has always a pure strategy best response. Okay, but in general there will be more than one pure strategy best response, and any convex combination of those pure strategies is also a best response. The thing that what happens in a Nash equilibrium is essentially that the other players, their mixed strategies are such that a player becomes indifferent between choosing his pure strategies, between a subset of his pure strategies. The weights get adjusted in such a way that I can now respond with any weighted combination of these, of a certain set of pure strategies. Okay, but that doesn't mean that I can actually play whatever I want, because I need to also choose my pure strategy in such a way that the others become indifferent in the same way, right? So everyone basically mutually confuses the other, kind of confuses or bamboozles the other player by making them indifferent between a subset of pure strategies, and that ambiguity is essentially from where the an equilibrium sort of arises. Okay, so each player is indifferent between this. So there's a particular point, but there is one particular point that makes the others also indifferent, and so on and so forth. And this holds for any n players. Okay, so this is the structure that always plays out in a Nash equilibrium. So in fact, this also suggests some ways of finding a Nash equilibrium. So for example, if you wanted to find a Nash equilibrium, okay, say for example, if I just let's write out one game here. So this is player 1, player 2. So this is non-zero sum, so I need two matrices to write out this game. So this is again for player 1, player 2. Okay. So I am now looking. So suppose this is matrix A and this is matrix B. Okay, and suppose I write out strategies for the players as y1, y2, z1, z2. So again y1, y2, z1, z2. Then I am effectively by a Nash equilibrium, I am looking for y star, z star, such that y star transpose A z star is less than equal to y transpose A z star for all y, and y star transpose B z star is less than equal to y star transpose B z for all z. Right. Now, if you think about how you would go about computing this, essentially what you would now need, if you see, what you would need is that you need to solve for these equations, and in each time you go about solving them, so you could try the following. See, for example, you could say, well, let me write my y star as y1 star comma 1 minus y1 star, and z star as z1 star comma 1 minus z1 star. Now, unlike before, we don't have this security type property anymore. So now earlier we were able to compute y separately and z separately. Now y and z have to be found together. So it is a simultaneous solution of these equations, these inequalities, right? So you have to find a z star in such a way that y star is optimal for this linear program, the first linear program for the player 1, and a y star such that z star is optimal for the second linear program, right? So it's the simultaneous solution that needs to be found. Now, one possible way of doing this is to say that, well, let us posit that each player makes the other guy indifferent between all his pure strategies. In this case, there are just two pure strategies, so let him make him indifferent between both those pure strategies. Okay. So suppose you say, well, z star should be such that player 1 gets the same payoff from both from either of his pure strategy. Okay, so that means 1 z1 star plus 0 times 1 minus z1 star. This should be equal to the payoff that he gets from his second pure strategy. That would now be equal to 2 z1 star minus 1 into 1 minus z1 star. and y star should be such that it does the same for the other player. So, y star is such that if you look at the payoff of the second player should now get indifferent, right. So, it is 3 y1 star plus 0 times 1 minus y1 star, that should be equal to 2 times y1 star plus 1 into 1 minus y1 star. Is this clear how I got this? So, this one comes from equating these two, okay, the expected payoff from these two, and this one comes from equating these two, this here. Is it clear? So, now what you have is actually just some linear equations which you can now solve to get to find y1 star and z1 star, and then from there you will get your answer. Okay. Now, the reason we could do this is because there were just two pure strategies for each player, right, and therefore here we had to just make, so you get just two equations like this. But suppose there were m pure strategies for for each player, and there were capital N many players, right, then each of these will not become linear equations. These will now become, this will all have the product of all the other players, because all the other players together make this guy indifferent, right. So, there will be a product of the probability distributions from the other n minus 1 players, and likewise there would be a product here for all players except for this player now, and so on. And you would have several equations because you are equating the payoff from each pure strategy, right. 1 equal to 2, 2 equal to 3, 3 equal to 4, and so on, because you are asking all of them to be indifferent between all those pure strategies. Here there are just 2, so you have just done 1 equal to 2. Okay. So, that becomes, therefore, then becomes a problem of solving for a solution of a high degree polynomial set of polynomial equations. But now if you can solve those, then you can get a Nash equilibrium there. But that need not be the only way of solving, because it is possible that the pair has become indifferent between some subset of them, like not all M strategies, but some subset, like he is indifferent between 1st, 7th and 10th, suppose, for example, or he is indifferent between 3rd and 4th only, something like that. So, what effectively then the search of Nash equilibrium then becomes even more complicated, because you need to write such equations by first selecting which strategies are to be chosen. Okay. So then it becomes a huge complicated combinatorial search. So, in general, computing a Nash equilibrium is actually quite a hard thing to do. Okay. So, it's not that straightforward to compute a Nash equilibrium even in these simple cases, because effectively you would have to do a combinatorial search by checking which subsets of strategies can you make every player indifferent between, and so on. And then after deciding that, you have to solve a bunch of polynomial equations. So, it's not that easy to do, but nonetheless the point is not about the computing something being hard doesn't make it invalid. Okay, the validity of the Nash equilibrium stands on much higher grounds than just the computational hardness. Okay, all right. So with this, I think we can conclude our study of Nash equilibrium in this kind of sense. I can maybe do one example next time, but from here onwards, then we will now go again deeper into information. Okay, we will look at many other issues such as communication in games and so on.